Hello everyone, and welcome to the second video in which we will be covering how to use bond enthalpies and average bond enthalpies discussed in the video 1 to determine enthalpy changes of reactions as we did with enthalpy changes of combustion and formation in previous lessons. I will explain it using the following example here. Consider the following reaction. 1 mole in which this reaction 1 mole of C2H4, which means 1 molecule of C2H4 reacts with 1 molecule of Br2 to produce 1 molecule of C2H4Br2. One thing you should notice is that they are all in the gaseous state. And since they are all in the gaseous state, one can use bond enthalpies to determine the enthalpy change of this reaction here. To determine the enthalpy change of this reaction using bond enthalpies, you should be able to draw these molecules. Thus, this is what I did here. I drew ethene, C2H4 over here. I drew 1 molecule of Br2, and I drew the resulting product over here, C2H4Br2. You should think of this reaction in terms of the reaction would proceed by initially breaking all the bonds in the gaseous reactants here. So we would break 4 moles of CH bonds. I would break 1 mole of C double bond C, and I would break 1 mole of Br bonds. Once these bonds in the reactants are broken, they would form gaseous atoms here. Thus, to form an energy cycle using bond enthalpies, we would always place the gaseous atoms over here, and the atoms that make up the reactants are the same as those that make up the product, so you can choose either or. I've chosen the reactants. I have 2 carbon gaseous atoms would form, 4 hydrogen gaseous atoms would form, and 2 bromine gaseous atoms would form here. And thus, in this direction here, these 2 arrows that link the gaseous atoms to the reactants represents bond enthalpies. Since these are all in the gaseous state and we have broken all the bonds present here into gaseous atoms, and thus we are breaking bonds here. Thus this process is endothermic, which represents bond breaking. I've broken once again 1 mole of C double bond C, I've broken 4 moles of CH bonds, and I've broken 1 mole of Br to form these gaseous atoms over here. The next step would be for these gaseous atoms to recombine to form in a different way to form the products over here. And thus if I've drawn the arrow in this direction to represent bond enthalpies, which is bond breaking, because if we were to go from this box over here containing the gaseous atoms to the products, this would represent bond forming. But I've done it according to the definition, and I've placed the arrow this way. Thus this arrow represents all the bonds in the products being broken to form the gaseous atoms over here as well. And thus we have 4 moles of CH bonds. I have 1 mole of C single bond C, and I have 2 moles of carbon bonded with bromine over here. And I've linked the cycle. All these values represent bond breaking and thus are endothermic, and I can simply get them from the data booklet as positive values and place them in the cycle over here. I've listed them over here, the values that are present in the data booklet, some of which are bond enthalpies and some of which are average bond enthalpies. Thus, the value for to break 1 bond of C double bond C is 612. So I would have positive 612 here. And the value to break 4 CH bonds would be 4 multiplied by positive 412 kilojoules per mole. These are listed in kilojoule per mole of gaseous bonds. The energy required to break 1 Br bond is listed over here as positive 193. So this arrow would be represented by positive 193. While to break the bonds in the products, over here we have 4 CH bonds. Thus this would be represented by 4 multiplied by positive 412. 1 C single bond C, which is positive 348 as listed here, and 2 CBr bonds, which is 2 multiplied by positive 276. And to calculate the delta H of this reaction over here, one would have to move from reactants towards the products through this cycle. Thus, these two arrows represent bond breaking. Thus, they would represent the bonds broken in the reactants to form the gaseous atoms. And these gaseous atoms would combine to form bonds, not break bonds, to form bonds in the products, and thus we would have to move against this arrow in this direction. This arrow represents bond breaking. In the opposite direction, it represents bond forming, and thus the sign of these values would have to be flipped. And this is done using the general equation as displayed below. Therefore, we would usually calculate we would usually calculate the enthalpy change of reaction using bond enthalpies by summing up the bond enthalpies broken in the reactants and subtracting them over here, subtracting them from the bonds formed in the products. This negative sign here is placed to change the bond breaking values obtained from the data booklets as endothermic values into exothermic bond forming values in the products. And thus normally what you would do therefore is calculate the bond enthalpies broken in the reactants and subtract them from the bond enthalpies formed in the products as stated here. I haven't placed the value for 404 CH bonds in these equations in the reactants and products because 4 CH bonds subtracted by 4 CH bonds would cancel out, and therefore I wouldn't list these values since they would cancel out. And I've only listed 612 plus 193, the energy required to break the bonds in the reactants, subtracted from the energy required to break the bonds in the products that remain, which are 1C single bond C, positive 348, plus 2 multiplied by positive 276. This negative sign would convert these into bond forming instead of bond breaking. And the answer would translate into, excuse me, it's calculated as negative 95 kilojoules per mole. Therefore, a quick recap. To calculate the enthalpy change of a reaction using bond enthalpies, the reactants and products must all be in the gaseous state. Always notice the number of moles here because this represents one molecule. If this were 2 moles of C2H4, then these bonds would all be multiplied by 2. I would have 2C double bond C and 8 CH bonds instead. But in this example, they are all 1:1:1 stoichiometric molar ratios. Since they are in the gaseous state, as stated previously, the cycle represents, to move through the cycle, we would always, to construct the cycle, we would always put the gaseous atoms over here and break all the bonds in the reactants and products as we did in this example and list them as well as their values. Then move through the cycle from the reactants towards the products, and thus I would add the values for the bond enthalpies broken in the reactants and subtract them from the values for the bond enthalpies formed in products, which translates to this main equation over here. It is usually easier to use this equation instead of constructing a cycle, but some students prefer constructing a cycle to make it more clear. This cannot be done unless the molecules Lewis structures are drawn to determine the number of moles of bonds broken in reactants as well as bonds formed in the products. I would like to give you another example, which I've listed over here. Allow me to fix this. In this example, the enthalpy change of reaction required for us to calculate is for that of the reaction of 1 mole of H2 molecules, 1 mole of H2, reacting with half moles of oxygen molecule to form 1 mole of H2O. Thus, the first step, as I stated previously, would be to draw all these Lewis structures. I've drawn 1 molecule of H, single bond H, plus 1 molecule of oxygen, double bond oxygen, O2, multiplied by half a mole, and a molecule 1 mole or 1 molecule of H2O. And I've constructed the cycle by placing the gaseous atoms that make up either the reactants or products, and as you can see here, these are all in the gaseous state, and thus bond enthalpies can be used to calculate them. I've listed the bond enthalpies in kilojoule per mole for a hydrogen-hydrogen bond, oxygen double bond oxygen, and an OH bond over here. Thus, the first step would be to break the bonds in the reactants. Thus, the energy required to break a hydrogen-hydrogen bond is positive 436 to form two H gaseous atoms, and to break half a mole of oxygen-oxygen bonds, and thus the value to break 1 mole of oxygen-oxygen bonds is positive 496, and this would have to be multiplied by half to form 1 oxygen atom. Excuse me. And I've also listed the energy required to break the bonds in one H2O molecule, which are 2 OH bonds, and 1 OH bond per mole of OH bond requires positive 463 kilojoules, and thus they were multiplied by 2, since we have 2 moles of OH bonds that require to be broken in this case. And to calculate the enthalpy change of this reaction over here, I would move through the cycle from reactants to products, and thus I would add the bond enthalpies of the reactants and subtract them from the bond enthalpy of the products, because moving in this direction, in the opposite direction, would change this sign over here into a negative, because this is bond forming, not the bond breaking in this case, because generally we normally break the bonds in the reactants, convert them into gaseous atoms, and these gaseous atoms recombine in a different way to form bonds and form the products listed on the other side. As I stated previously, we can simply use this equation over here for when using enthalpy changes of when calculating enthalpy changes of reaction using bond enthalpies for reactions occurring in the gaseous state. Thus, you would always sum up the bonds broken in the reactants, which is positive 436, plus half multiplied by positive 496, and subtract them from the bonds formed in the products, which is 2 multiplied by positive 463, excuse me, which gives an answer of negative 242 kilojoules per mole. If this were 2 mole of H2O molecules formed, then I would draw 2 molecules of H2O, and I would count the number of bonds I would break, which would be 4 OH bonds instead of 2. But in this case, it's also 1 mole of H2O. I will be giving you one more example in the third video, in which the number of moles or stoichiometric ratios are not all 1-to-1 or half moles. Thank you for watching. Please proceed to watching the third video.